Okay, hello everyone. Welcome to my talk. My name is Tian, and I'm a postdoc, currently a postdoc at Simon Fraser University. This is a joint work with my supervisor, Professor Michael Monaghan. And this year I had a great opportunity working at Maplesoft on site for a couple of weeks, for 1 week, and then try to implement my code into Maple, and hopefully it will be released very soon in Maple 2026. Thanks to Dr. Jürgen Gerhard at Maplesoft. Okay, I'm going to start with describing the problem I've been working on since I was a PhD student. Problem P, given a polynomial, multivariate polynomial with integer coefficients, the goal is to compute the irreducible factors of A, also with coefficients in Z. So we do not factor the integer content. So my research centers on the design analysis and to solve problem P. Just a very a brief history of multivariate polynomial factorization. The main tool is sparse Hansel lifting. So in 1975, Wang's algorithm called multivariate Hansel lifting. This was the classical algorithm to factor a multivariate polynomial. However, his algorithm can be exponential in the number of variables. So in the 1980s, Zippel and Keltoffen both gave sparse Hansel lifting algorithms. In 2016 and 2018, my supervisor and the previous PhD student worked on this sparse Hansel lifting again, and they improved upon Keltoffen's algorithm. So the new algorithm was called MT-SHL. 2020, I began my PhD work already, and I was able to improve upon their algorithm and the 2018 version of the sparse Hansel lifting, and I made it highly parallelizable. However, the problem was so the dominating cause, that's what we found, is evaluating the input polynomial. So what we decided to do was to use a black box representation for the input polynomial. I will give a definition of that later on. So from the black box approach, again, pioneer work was by Keltoffen Trigger in 1990, and later on, Rubenfeld and Zippel tailored their algorithm and had an algorithm just for factoring a polynomial in the ring of integers. So Keltoffen and Trigger's algorithm was for factoring a polynomial with integers with coefficients in a field. So their approach. So in 2022, I gave a new approach. So it's I'm not using their algorithm, but improved. Modified my own algorithm. We call it CMSHL, and use that for modified, and so we'll be able to import a black box polynomial. The advantage was that it requires significantly fewer probes to the black box than Rubenfeld and Zippel's algorithm was the best known algorithm as black box factorization. So these were publications I made, which were milestone contributions. The first one was non-black box in 2020, and then 2022 and 2023. The first one was for monic and square-free case only. And then 2023, I was able to present at ISAC. The paper was already considered non-monic and non-square-free case. So I graduated in 2024 with a lot of details with complexity in analysis, with failure probability, as well as the algorithm description and a variety of benchmarks that we tested. This year, I've been working at Maplesoft for implementing the algorithm, also considered a large integer case, and other problems of applications that I have not finished. So it's an ongoing project. So I'm gonna start with the definitions. So what is a black box representation of a polynomial? A sparse representation, this is easy. That is just can be written by a formula. However, a black box representation is implicit. So since our algorithm is modular, so we use a modular black box, which is just a computer algorithm, a computer program that input an evaluation point alpha, and then also a prime p, then it outputs the evaluation f alpha mod p. So this is going to be the input into our factorization algorithm. And so, for example, if we want to compute the determinant of a symmetric Toy-Place matrix, then the modular black box can be just coded in Maple as a procedure. Then if I call this procedure with the evaluation point and the prime, let's say a very small prime 7, and this is the answer. Okay, so as I already mentioned, earlier work by Rubenfeld and Ziebel, their black box factorization algorithm first computes black boxes of the factors and then recover the sparse representation using a sparse interpolation. Our algorithm does the factorization that outputs the sparse representation directly. So we call this approach number 2. Their algorithm, and there's also a Cato-Finn and Triggers algorithm. They are both approach 1. Okay, so I wanna let everyone see that there are 2 advantages. So first of all, the algorithm is space efficient. So for example, let's consider this Toy-Place example again, that the number of terms in the expanded form of the determinant is a lot greater than the number of terms in each factor. So it's space efficient. Also, it requires fewer probes to the black box than the Rubenfeld and Ziebel's algorithm. So this was a result published on ISAC 2024, just in the poster section. I think I also coded Rubenfeld and Ziebel's algorithm recently that in practice, I think it requires more probes to the black box. Also, they also need their algorithms also requires a lot of univariate factorization, which our algorithm only need 1 at the very beginning. So this is an example. I don't know how much time I have, but the program chooses an evaluation point and the prime, and it factors in, first of all, reduces to univariate and factors it, and then the sparse tensor lifting recovers 1 variable at a time. And this is the true factors at the end. I want to present a benchmark. This was a earlier benchmark to compute the Toy-Place determinant. And a fast van der Waals solver was implemented, and so I think I was the first one to be able to actually get T in 16, and it only took a little bit longer than an hour. When n is greater, so n is the number of variables. When n is greater than 14, then our algorithm already outperformed Maple and Magma. So this another benchmark, which these are Dixon matrices, and so n is the number of variables, the size of the matrices, and the degrees, partial degrees in each variable, number of factors R, the number of terms in each factor, exponents, and the number of terms in the determinant if in the expanded form. So we can see that, for example, here on 4D, that there's this is number of terms in the of the determinant is huge. So it took 43 seconds to compute that. However, Maple ran out of memory when it tried to compute it determinant and then factored it first. It tried to compute the determinant first and then factors it. I think I wanna. Okay, so integration into Maple. Then now there's it's not been released, but I've been designing a module, and then so the code BB factor can be called by the user. B is a black box, so the user has to input it. Also, there's another option to just input a matrix. And what's inside the BB factor is quite complicated, computing partial degrees first, and then 3 layers of code with Hansel lifting, and then finally check the answer probabilistically. So I think that's the slides, and I just want to quickly demonstrate my code. Hopefully I have time to do that.
You're about at 12 minutes now.
I'm at 12 minutes. So first example, please. I wanna just run the 3, and so so with black box factor, and then import a matrix. Then there's a piece of code to create a black box, and then import into BB factor. Then the algorithm starts. BB factor it does one Hansel lifting at a time, recovers one variable at a time, and then it counts how many probes to the black box and gives the final answer. Also checks with the right answer, which is okay. Also, there are different options. So the user can also choose to only output the primitive factors, which is this option, primitive equals to 1. And also another option to use Maple code or C code for some subroutines. And these are just the primitive factors. I think I'll just show one more. Let the author see tuplets. Okay, so what happened here? Again, this is a 5x5 tuplets, and the answer here, and also a check with Maple's determinant and factor commands. This timing is for Maple, and my timing was not. It did not outperform the Maple since the matrix was not big enough. I think I'm probably better stop here.
All right, thank you, Dr. Chen. Let's thank the speaker.
Yeah.
We have about 1 minute for if anyone has a question in the chat, or you can just raise your hand.
There are no questions in the chat. I was wondering if you could give us a very broad idea of what allows you to do the direct step from the black box input to the explicitly given output factors. Is there anything you can say about that in 30 seconds, or is that too complicated?
I just discovered a step in my algorithm that I'm not asking everyone to read it, but the step 8 in here, this was the only step to the need of probing the black box. So I just changed the code from well, it sounded simple, but not quite. Changed the code from a previous non-black box version to just do a bivariate interpolation, and then reduce the cost significantly. That was simple. Hopefully, it sounded simple, but anyway, a lot of work involved with this.
I can imagine. Thank
Yes,
you.
it looks like it. Okay, let's thank Dr. Chen again. We're going to move to the second speaker, Dr. Richard Hollister. Could you please share your slides?
I do need to unmute myself.
And unmute, yes. So Dr. Richard Hollister is our next speaker from Sweetbriar College. So please go ahead.
Yeah, thank you. To go to full screen, there we go. I'm going to be talking about some, albeit a little bit more theoretical right now. So I'm a theoretical mathematician. I'm not a programmer. I'm not a computer scientist. So this is my first time delving into the world of Maple since 2012 when I was an undergraduate, using it in my undergraduate classes. So it's been a while. So go easy on me when it comes to the Maple code. So I'm going to be talking about some Maple procedures that I'm developing for quasi-triangularizing matrix polynomials, and there are a lot of steps that involve additional results in the matrix polynomial world that I'm looking to implement in Maple. So I'm going to give a brief background on matrix polynomials, talk about what the heck I mean by quasi-triangularization, and maybe a little bit about how that works theoretically, and then I hope to get to a demonstration of the primitive code that I have so far for implementing this in Maple. So first things first, matrix polynomial is a matrix with polynomial entries. It's a pretty straightforward definition. We say that a matrix polynomial is regular, essentially if it's square with a non-zero determinant, right? So the determinant is a polynomial in the indeterminate. So if the determinant is identically zero, then we say it's not regular. Okay. Regular matrix unimodular if the determinant happens to be a scalar, a constant, and we need that for the main tool that is used in matrix polynomials is the Smith theorem, which essentially gives us a way to diagonalize a matrix polynomial by multiplying by some unimodular matrices. So you start with a matrix polynomial. There are some unimodular matrices that you can multiply by in order to get a diagonal matrix where the diagonal entries are polynomials that satisfy a divisibility chain. And so the Smith form is unique for each matrix polynomial, and this is implemented already in Maple in the matrix polynomial algebra, and I think also in the linear algebra packages. So when it comes to matrix polynomials, there are several invariants that we like to study. The first of which are eigenvalues. Finite eigenvalues. So these are the zeros of the invariant polynomials in the Smith form. So the polynomials that appear on the diagonal of the Smith form, the zeros of those are what we call the eigenvalues. There's also the possibility when we have a matrix polynomial for infinity to in some way show up as an eigenvalue. Right, so we have the possibility of an infinite eigenvalue, and the multiplicities that are associated with that are called the structural indices for the infinite eigenvalue. And this is in some way related to degree deficiencies in the invariant polynomials. The last invariant, which is not really related to this talk, are minimal indices that have something to do with the left and the right null spaces of the matrix. But I'm not going to go into that because it's not relevant for this talk. What I'm going to be focusing on are matrix polynomials for now that only have finite eigenvalues without any, there's no infinite eigenvalue and there are no minimal indices. So we're just going to be focusing on the invariant polynomials in the Smith form. So there are a couple problems in this field that are well studied. You have the forward problem of here's a matrix polynomial, compute all of its structural data, right? And there are lots of results on how to do that efficiently. And what I'm interested in, though, is the inverse problem, right? If you give me a list of some data, can I come up with a matrix polynomial that has that realizes that data, right? So if you give me a list of either invariant polynomials or eigenvalues, can I come up with a matrix polynomial that has that data? And there are also a lot of results along this line that have various combinations of data. So if you just want to specify the eigenvalues, the finite eigenvalues, or if you want to specify the finite and the infinite eigenvalue data. So there are a lot of results that have different combinations of the data with and without additional constraints. Such as one additional constraint would be if you wanted a specific degree of the matrix polynomial. Okay. So what I'm interested in doing is solving an inverse problem where I have an additional constraint that the matrix that I give you is quasi-triangular. So that just means that it's a block triangular matrix. So all of the block matrix, all of the blocks below the diagonal are 0. And so the main problem that I'm going to be talking about here is if we have a list of invariant polynomials factored into irreducible divisors, can I give you a quasi-triangular matrix that has that data? So a couple things to keep in mind: we're not necessarily working over a closed field. If we were working over a closed field, then I could guarantee a triangular realization instead of quasi-triangular. So if we relax to any field, then we can't guarantee triangularity anymore. We have to go to block triangular. Whoops! Whoa, that was way too far. So as I said before, I'm only going to be looking at the invariant polynomials factored into irreducible factors. So there's no data at infinity, no eigenvalue infinity, no minimal indices to worry about. And I'm also going to be going for a target degree. So here are some key results that we'll be using. So the first result is a general realization theorem proved by Bertrand Teguia and Van Duren. So this just says you give a list of data that satisfies a very simple constraint that I'm not going to go into, then it can be realized, and they have an algorithm for doing that. And then the specific problem that I'm trying to implement in Maple is that you give a list of regular data. So that means that we have possibly infinite eigenvalue data, and we have irreducible divisors of the invariant polynomials. And you give me that data along with a choice of degree, and I can produce a quasi-triangular matrix that has that data. So that's the goal of what I would like to do in Maple. So I want to go through a quick example that I will reflect in the Maple code that shows sort of how this works. So we start with the invariant polynomials. I have them here conveniently factored for us already, so we don't have to go through that step. But factoring is required at some point along the line. So we start with a list of the invariant polynomials. We have some higher degree irreducible factors involved. So that's going to give us some larger diagonal blocks. The first step that we do is we rearrange them so that the degree differences are as small as possible. Let's put it that way. So that's just rearranging them so that we can move these irreducible factors around, right? So we're taking one factor from one polynomial, moving it to a different polynomial. So we're rearranging the factors so that the degree differences of the polynomials are as small as possible. And this can be done in a way that preserves the invariant polynomials. The next step is to essentially group the polynomials into groups that have equal average degrees, right? So this is the combinatorial process that in this case we're going for an average degree of 2, right? So we have two polynomials of degree 2, so they're left alone. And then we have a grouping with a degree 1 and a degree 3, and then a grouping with 2 degree 1s and a degree 4, so that the average comes out to be 2. And now what's going to happen is we take the original Smith form, the diagonal matrix with the invariant polynomials down the diagonal, and we apply these different rearrangements in a way that preserves the invariant polynomials. So this is done by doing unimodular transformations of the Smith form. And we end up with this block partitioned matrix. It's not that far from being diagonal. We do have some non-zero entries in the off-diagonal blocks. And then the next step is to apply the fundamental realization of dopey code Bertrand and Van Duren to each of the diagonal blocks to make them have degree 2, right? Because currently the blocks have degree 4, degree 3, and 2 1-by-1 blocks of degree 2.
So
And
you're
so
about 12 minutes now.
This is what it looks like when we do that. All right, so I want to go ahead and escape out of this and go to my Maple code. Let me try and zoom in a little bit. And I'm just going to run through this with it's the same example from the slides. So we have our list of invariant polynomials. And again, forgive my Maple coding. I'm not the best at this. So we have our original list of invariant polynomials. When we run through the procedures here to arrange the diagonal into those polynomials that have their degree differences as small as possible, this is what we get. These are just some intermediate procedures. And so now I have them rearranged into the groupings, the blocks that have equal average degree. Sorry, let me. get through that. This is the actual implementation when we apply the transformations to the Smith form to get that target diagonal that we had before. And then finally, more of that. Finally, we have our quasi-triangularization that goes through and fills out the diagonal blocks by multiplying by unimodular matrices, so that we can now see that the diagonal blocks are all degree 2. Right, and we have a 3x3 block and a 2x2 block. And that's basically what I have so far. I am very much looking to expand on this code to apply to a more broad setting, because right now there's no data at infinity that's being taken into consideration. So I'm looking to expand on this code. I'm not a very good Maple programmer, so if anybody wants to help me, please let me know. All right, I'll stop here.
All right, thank you, Dr. Hollister. Let's thank the speaker. So we're kind of out of time, unfortunately, for questions. So I'd suggest if people have, or the call for help, I guess, is there some kind of networking, or at least they can message in the chat. So let's move to the third speaker, Bertrand.
Yes.
And yes, we can hear you. Please share your slides. Yes. Okay, so our third speaker is Dr. Bertrand Teguia Tabuguia from Oxford University. Please go ahead.
Thank you. Thank you for having me. Hello, everyone. I want to discuss D-algebraic sequences. I will present a software package that I call DalgSeq. And let's start. Yeah. So for the introduction, I will define what I call a D-algebraic sequence. Consider, for instance, this recurrence equation here. I believe most of the people in the audience know this. This is the equation of the Fibonacci sequence. So if you start with 0, 1, or 1, 1, you will generate all the terms of the Fibonacci sequence using this recursion here. So let's call this ADE Fibonacci. And this is another recurrence equation. Here you can see the square in the equations. They are exponents. And these are, so I'm considering all type of equation where the expression is a kind of polynomials in several terms of the sequence. So this is basically what I call a D-algebraic sequence. So formally, a definition will be, if a sequence, say Sn, is D-algebraic, then there exists a multivariate polynomial such that for finitely many consecutive terms of the sequence, you can have this equation here. And such an equation is called an algebraic difference equations. This is where the D comes from in the D-algebraic. And here are examples of algebraic difference equations. So here the order for the Fibonacci is 2 and the degree is 1. And for the ADE square root, this is the equation for the square root. The degree is 2 and the order is 1. Okay, these are examples. And now I want to talk about a sub package of this package here. So this is the package is called NLGE. It stands for nonlinear algebra and differential equations. So I want to discuss this sub package here. It's a sub package of the big package. Here is a diagram of the package. NLG is a package initially built only for D-algebraic functions satisfying differential equations that are polynomial. And in that package, you have commands like arithmetic D-algebraic functions for computing differential equations for arithmetical functions that satisfy similar equations. And you can compose them. So you can compose, for instance, exponent, let's say arctangent and exponential. If you have differential equations for the two functions, then you can construct the differential equation for the composition using this command. You take the equations of the two functions and you compute a differential equations for their compositions. You can also compute for the rest, the inverse, the functional inverse. Like if you have the differential equation for exponential, you can compute the differential equation for log. You can
Bertrand,
differentiate.
could
Yes?
I ask if you could zoom in a little bit? We got a request in chat if you would be able to zoom in a little bit.
Is this okay? So, is this better?
It probably won't help much for the image, but this way the rest of the. Thank you. That's great. Yeah.
Oh, okay. Yeah. So I want to discuss the subpackage DalgSeq. Multi-DalG is for multivariate functions, and ANZAT is different techniques for dealing with the same kind of functions. And if you want to access the package, you can download it via this link here. This is the GitHub repository of the package. You download the file nlde.mla, and you use it as any software package in Maple. Now let's load the package DalgSeq. Here are all the commands currently available in the package, but I will be discussing only a few of those, like 4 commands in the package. I hope everybody can see this. So we are going to do the arithmetic. We have initially we have considered, this is not needed, these 2 different equations for the Fibonacci and the square root. Suppose you want to compute a recurrence equation for the ratio of the nth term of the square root sequence and the nth term of the Fibonacci sequence. I'm not interested in the initial values. I just take the equations for the Fibonacci and the equation for the square root. So I put the equation for the Fibonacci here, the ADE Fibonacci, ADE square root. Here are the nth term of the sequence in the equations. So I will call the unknown sequence in the resulting equation U. So if I just use this command from the DalgSeq package, arithmetic DalgSeq, and then I type, after a few seconds, I got these different equations. So you may ask, what is the degree and the order of this equation? There is a command for this. You call order degree recurrence. And with the unknown sequence UN, you type this, and you find that this one is a difference equations of order 3 and degree 8. Now you may want to do more. Suppose you have the Fibonacci sequence and you are interested in the recurrence equation for this expression here that depends only on the Fibonacci terms, like the nth term. Here you have the square of the Fibonacci sequence, the product with the next term. So you have this polynomial expression that depends on shifts of the Fibonacci sequence, and you want to know what kind of equation does this satisfy? What is the algebraic difference equation for this expression here? And then you type, you find that it is C-finite. Actually, this big expression here satisfies a constant coefficient linear recurrence equation. And yeah, so what this says is that if you solve this equation in terms of Fibonacci, you will find that there are solutions that are written in this form in terms of the Fibonacci sequence. So this is for the arithmetic, some of the operations that can be done using the package. So now let's discuss rational recursion. Yeah, what I call rational recursion is that if you have a sequence and you can write the next term in terms of as a rational functions of the previous terms of the sequence. With the Fibonacci, this is clear, but in general, the question here is to convert some sequence that are known as rational recursion. These kind of sequences are sometimes needed in computer science for finite automata, so for some kind of automata. So now I want to maybe ask, is it possible to compute such a recurrence equation for factorial n, or factorial n squared, or factorial n cubed? When I started working on this problem, initially it wasn't straightforward to see. So I know factorial. Yes, I have this equation for factorial, for instance. I know that the next term is the n plus 1 than the n plus first term is n plus 1 times the previous term. We have this recurrence equation for factorial, and I want to find a recurrence equation that is independent of the index variable. By the way, such an equation is called a holonomic recurrence equations. The coefficients are polynomial in the index variable. So I want to find a recurrence equation for this that is independent of this index variable, and that writes the next term as a rational functions of the previous one. I can start with this equation and compute this rational recursion here. And this is correct. So you can plug in factorial n and factorial n plus 1. You will see that the both sides coincide. You can do the same with factorial n squared. There is a rational recursion for the nth term of this sequence. You can do the same also for factorial n cubed and find this rational recursion here. So you may see, maybe you are doubting that maybe these are not correct. You are just computing stuffs, but we can check in Maple. Suppose we plug in this rational recursion here. This is 316. I hope this is visible for the audience. So I will substitute n plus j factorial to the cube for j from 0 to 4 in this equation, left-hand side minus right-hand side. So I should compute this and obtain 0 to check that this is correct. And yes, it is correct. It's not just about computation. There is actually a theorem proving that in general, for every holonomic equation of order, let's say for order R and the polynomial coefficients of some degree D, we can always find such a rational recursion of order R plus D. And the theorem can be found in one of these, in the two paper here, this paper and this paper. And yeah, this result was also generalized to a more general class of sequences. Here the sequences are called C2 finite. What it means is you have a linear recurrence equation where the coefficients themselves satisfy some kind of linear recurrence equation with constant coefficients. Like for instance, you can have coefficients here that are the Fibonacci sequence, the Lucas sequence, and all this kind of sequences. Here is an example. I couldn't find something simpler. I just take one randomly, not very, very randomly, but yeah, I took one equation, this equation here, and I call it C2 equation. I put it in C2ec. In the equation you have un, which is a coefficient satisfying this recurrence equation here, and Vn satisfying this second order recurrence equation. So they are both C2 finite. Then in the package, I use the command cc finite to simple radweg. These rational recursions are called simple rational recursion in this paper. Yeah. So we took the same name to call for the name of the commands. And here I will use, I put the equation, the C2 finite equation, the Ognon sequence, the coefficients, and their terms here. So, and I run the package, and I compute this rational recursion. This is a rational recursion of order 6, and you have here the numerator and the denominator. Yeah, so this is these are the highlights I wanted to present for my package. I hope this was clear to the audience, and I want just to thank you for your attention.
All right, thank you, Bertrand. We have about 3 minutes for any questions. So you can either unmute, raise your hand, or post in the chat.
No questions in the chat. If anybody wants to ask a question, they can unmute themselves and ask it now. Or otherwise, I wanted to ask, so I think these D-algebraic sequences are currently not supported otherwise in Maple in full generality. Is that correct?
Yeah, that's correct. It's not, yeah, not in full generality. Yeah.
Do you know if there are any other packages that support the working with these D-algebraic sequences?
I think in Maple, in Maple, I don't think there is. Maple has almost everything about holonomic sequences with, recurrence equation with polynomial coefficients. But for the algebraic sequences, not really. There is, for the algebraic functions, there are some packages in Maple like differential algebra, Thomas decomposition, that can be used for the differential case. But in the difference case, they are not. I'm not aware of any package in Maple that does this. Yeah.
And in other software packages, do you know if there are Python or Mathematica?
I'm aware of one, but for the C2 Finite, they have an implementation in Sage. So I'm aware of one package developed by people in Risk for sequences. Yeah.
And do you know if the package you're currently presenting, does that support particular operations that are not supported by the existing Sage package, or is there overlap or differences that you can?
There are differences. So I think the questions, the operations in this package here are almost all different. So there is only one maybe in the computation of the algebraic difference equations. The package there has a command for computing in a differential case, for computing the algebraic differential equations from a system of DD finite, the differential analog of C2 finite equations. But the algorithm there is not, so the purpose is not to find a rational recursion, but just to find an algebraic differential equations. And that, the method can also, it's a bit similar in some cases in what I do here.
Okay, thank you again, Dr. Teguia. So we'll go to our last speaker. I guess it's Dr. Rashid Barket.
Yeah, perfect. Thanks. Let me just share my screen.
Okay, and Dr. Barket is from Coventry University. So please, the floor is yours.
Perfect. Thank you. Hi, yeah. So I'm currently in the last year of my PhD, and I am working at Coventry University, but also with Maplesoft. My PhD is actually sponsored by Maplesoft. So this work with my supervisors, Matthew England and Jürgen Gerard, is about how to use machine learning to improve symbolic integration within Maple. And the way that we're going to improve it is not through trying to use machine learning to predict answers directly, but trying to improve existing software within Maple. So the way that the integration function in Maple works currently is it's essentially a meta algorithm where there are 13 different methods available at the top level to the user. So at the bottom of my screen here, you could see that if I want to integrate the expression sign of x and I ask for all of the methods to return their answers, we could see which ones were successful and which ones failed. The ones for lookup and default, for example, are the answers you would expect when you're learning calculus in the first year. But for example, the answers from Norman and Meyer-G look a bit more complicated. Norman introduces the tan function, whereas Meyer-G introduces square roots and the pi symbol. So even though all of these answers are mathematically equivalent, some are more understandable to the user versus other methods that are not so understandable. So what our goal is that we're looking to use a machine learning model to select the method that will output the best representation of the answer, or you could say the most simple looking answer. So due to time constraints, we're not going to actually go too deep into the exact machine learning methods, but we're going to talk about how we improve them using some features of math expressions. So again, that is kind of the overview, but One very important thing here is that we also want to be doing better than Maple using machine learning, because if what Maple is currently doing to select the best method is already doing as good or better than machine learning, then there's no point in trying to implement this machine learning model. So we're going to introduce different ways that we could represent math expressions to machine learning models. And we're also going to explore how the way we frame the problem in terms of machine learning can affect the success of how well the machine learning model does. So there are kind of three different ways that you could represent a math expression to a machine learning model. The first one, which you see on the left here, is a text sequence. So for the expression at the top here, what we did is we put it in its prefix notation, or also known as Polish notation. You could kind of read it from the bottom up, where you take the 2 and x, and you see that there's a multiply sign here, so that's 2 times x, and you can see that's the argument for the cos here. If you read it from the bottom up, that's kind of how you get this tokenization of a math expression. However, this text sequence doesn't capture the inherent relationships between the operators and the operands. So in the middle representation here, we can represent math expressions as trees, where the leaves of the tree are variables, integers, and constants, and the inner nodes of the tree are the operators. So in this tree representation, you get more of an explicit representation between how the operators and operands connect to each other. Kind of the last representation is a feature vector, where you could kind of think about if I were to extract features from the math expression and put them into an Excel spreadsheet, then this is how the representation would look. However, we kind of focus on the first two representations because the last representation requires a human expert, and also this representation isn't as useful for current machine learning architectures, which we'll talk about in a bit. So if you've done any machine learning before, you'll know that you need a large corpus of data to train on. So in this case, what we need to do is we need to take an existing integrand, like we saw at the beginning of the presentation, for example, sine of x, and then we need to label that data, f of x, with which methods are successful and which are not. Now that's not too hard. What we could do is we could actually pass this function through Maple and then label the methods as, oh yes, the first method was the most simple looking answer. The second method did not have the simple most looking answer. And then we could go down the list of the 13 methods. However, there is one problem where you actually need your f of x to be integrable. Otherwise, all of the methods are going to fail. So just randomly creating an expression won't always succeed. In fact, most of the time you may generate an expression that will not be elementary integrable. So back in 2020, there was a research group from Meta who kind of worked on a similar problem and came up with 3 different data generation methods that you see as the first 3 here. So these methods kind of had biases themselves, and we sought to address those biases in the data by coming up with these 3 data generation methods at the bottom. Now, I'm not going to go into the details of them because that could be a whole talk themselves, but just know that these 6 data generation methods all work to produce an expression f of x, where we then put it through Maple, and that's how we get our labeled data. So one of the models that is commonly used, not just in machine learning for mathematics, but machine learning in general, is a transformer. Now, a transformer is, as most of you know, kind of the theoretical backbone of large language models like ChatGPT. A lot of research has been done into exploring how transformers can be used to solve math problems. Now, the problem with transformers is that they'll take in the representation like you see on the left with the text sequence. But again, as I mentioned before, this text sequence does not capture the inherent relationships between the operators and the operands. So what we did is we tried to represent, rather than the text sequence, tried to represent the math expressions as trees, where we pass these binary vectors to the transformer so that it has this information before making its predictions. Now, the way that you can understand this is that you always push a length 2 vector onto the stack whenever you want to represent a node in the tree. So the root node would simply be the 0 vector, but then we could represent the left and right children of the root node by either saying the 1, 0 vector gets pushed onto the stack, and that's the left child of the root. And here the 0, 1 represents the right child of the root. Now we could keep going down this tree. For example, the power operator says you're the left child of the left child of the root. And if we look at 2, for example, we're saying we're the right child of the left child of the left child of the root. So when we pass these kind of positional information to the transformers, then they get to understand these math expressions in more detail. So the first task that we did was we wanted to just use 2 types of machine learning models, the LSTM and transformers, and also their tree variants to see if we do better than Maple at, again, predicting the most simple output. Now, there's 2 things I want you guys to observe here. The first one is that all our machine learning models are kind of doing better than what Maple is currently doing at selecting the best answer. But this comes from the data generation methods, the 6 data generation methods that I talked about. Now, since I'm sponsored by Maplesoft, what we had access to was actually their in-house test suite of integration functions. So this is a collection of roughly 13,000 different functions. It's bigger than that, but we took a subset of 13,000 different functions where they fit our machine learning needs. You see here that machine learning doesn't do a lot better on the Maple integration test suite compared to Maple here. So in the data generation ones, we're getting about just under 10% better than Maple, but in the Maple test suite, we're not doing so much better. We're about doing the same as Maple. But another thing, again, was about the trees. So you could see here that the tree transformer is doing better than the regular transformer, and the tree LSTM is doing better than the regular LSTM. Now, what we want to do is address the right graph here. How do we do better on the Maple test suite? What we did is we changed our formulation of the machine learning problem from a classification problem to ranking. Now, ranking is commonly used in recommender systems. You could think of recommender systems as, for example, if you're using Google search, it is a recommender system where it outputs a list of most relevant items. If you're on Netflix, for example, then Netflix is going to recommend to you what items you think are most relevant to what you want to watch. So in our formulation, we want to recommend to Maple which methods we think are going to do the best and which methods we think are going to do the worst. So with our labeled data set, what we do is we do this pairwise comparison. So that is for each pair of methods in the sample, we compare if method I did better than method J. We feed that to our machine learning model. It makes a prediction. And if it got the prediction correct, we reward the model. And if it got that prediction wrong, if it predicted that model J was doing better than model I, then we punish the model, and it learns to understand the relationship between which methods are supposed to go at the top of the list and which are going to go to the bottom. Now, when we change our formulation to ranking, you can see that we do a lot better in this situation. In the data generation, in the data generators where we had a held out test set, the tree transformer, which is our best model, was doing over 20% better than what Maple is currently doing. But like we said before, we wanted to do better on the Maple test suite because that's a data that our model has kind of never seen before. It shows that we could try and generalize better. And here we could see that the tree transformer is doing now 13% better than what Maple is currently doing. So a big improvement from the binary classification formulation. What's even better is because we're doing this as ranking the methods from best to worst, even the answers that are getting close to the best answer start to get a bigger jump as well. So if we're getting answers that are about 10% as close to the optimal answer, we're getting over 15% better than what Maple's currently doing. So now we could see that the machine learning model is doing much better and able to generalize a bit better as well. So in this table here, you could see some examples where the integrand is the left column. The middle column is what Maple currently outputs as the answer. And the right column is what our best model, the tree transformer, is recommending as the best answer. So for example, for the first row, we're actually able to get rid of the trigonometric functions in the answer and just have the answer represented as a function of r and x. In the second example here, Maple introduces a lot of new functions and introduces the dialog function, square roots, imaginary numbers, whereas our answer only introduces one new special function. Another interesting example is the middle one, where Maple suggests this much more complicated fraction when we actually know that the answer is just x. So you could see through these examples why it might be better for the user if Maple is able to output an answer that is more understandable.
You're about at 12 minutes.
Okay. Yeah, perfect. So just to conclude, what we did is we tried to use machine learning to predict the best answer in symbolic integration. We compared what is currently the standard in machine learning for mathematics, which is just the regular transformers or sequence models, and compared them to the tree models. We could see that the tree models are doing better than the sequence models. And also, when we switched from this ranking, when we switched from just strictly predicting are you the best method or not, which is classification, to this ranking paradigm, our model was able to get better results both on the in distribution and out of distribution data, which was the Maple test suite. So that is the end of my presentation. If you want to see the preprint of the paper, you could go to the link there or just Google the title of the abstract. I'm currently working with Maplesoft developers to try and possibly get this as the current standard for the dispatcher for the symbolic integration function Maple. So this might be something that you could see in a future iteration of Maple. Thank you.
All right, thank you, Rashid. All right, we have just about a minute or two. There's a question from Rob Corliss in the chat. Any plans for, you wanted for years to have a version of this for simplification, not just integration. Any plans for something like that?
Yeah, Rob, that's a very interesting question because I'm near the end of my PhD now, but actually the original proposal for my PhD was to work on both integration and simplification. So what we had wanted to do originally was also have some sort of machine learning model that can predict which steps to use in simplification and try and get to its most simplest form. So unfortunately, did not get to that during my PhD, but I do have ideas for how that could be tackled.
Excellent. I look forward very much for it.
Okay, any final quick questions? If not, then we'll bring the first algorithms and software stream to a close.